Hi. Let's try to multiply some two-adic numbers. We can do it the same way as we would multiply finite binary numbers, except in this case we may never run out of digits. So let's take a number that we know that has infinitely many ones in its representation. This is -1. And let's multiply it by, for example, 5. So first we need to multiply this entire number by this digit 1. So this is going to be simply a copy of this number, -1. Then we multiply by the second digit, which is 0. So we have nothing here. Then we multiply by the third digit, which is again a copy of the number, but shifted here 2 positions to the left. And there are only zeros left. So this is going to be all zeros down here. And so on. Now the result is the sum of these numbers. So first we have this 1, then we have 1 plus 0 is again 1, 1 plus 1 is 0 and 1 goes into carry, 1 plus 1 from carry is 1, and so on. So the result is indeed -5. And we can also write this second number as a column here, because each row is corresponding to a single digit of this second number. So we have copies of this number only in the rows that correspond to digits 1 in the second number that we multiply. And also each is shifted left according to the position of this digit in the second number. We can see here that, for example, to compute first the lowest 4 digits of the product, we only need to know the lowest 4 digits of this factor, because here we never look at the higher digits when we are adding them. And we also need to know only the lowest 4 digits of the second factor, because anything that is multiplied by higher digits is shifted left so far that it doesn't affect these lowest digits here. On the other hand, if we consider how many digits the product may have before we reach the repeated sign bit, for example, in case of addition or subtraction of 2 numbers, we needed 1 more digit. And here, for the product of 2 numbers, we need twice as many digits as the larger size of the 2 factors. So, for example, an x86 architecture has a mul instruction for multiplication, and it multiplies 2 values, for example 32-bit values, and computes a 64-bit product, twice as many digits. Or if we multiply 2 8-bit values, 2 bytes, then we get a 16-bit result, always twice as many digits. And thanks to that, we never have an overflow. but also to know twice as many digits of the result as we have digits of the factors, we need to fill the upper halves of the factors with the sign extended bit or with zeros, depending whether this is zero extension or sign extension. And for this reason, we have two different instructions for multiplication. This one is for unsigned multiplication, so it extends the number with an upper half that is all zeros when it multiplies, and this one does the sign extension, so the upper half of the number for the multiplication is filled with the sign bit. Let's say that we have an 8-bit multiplication here. We need 8 bits. And now we are going to compute the product that has twice as many digits. So for 8-bit multiplication, we are going to make a 16-bit product. And depending whether we do a signed multiplication, then we are going to use this upper half filled with the copy of the signed bit. Or when we do an unsigned multiplication, then we would simply use zeros here. And the same goes for the second number, because we also need 16 bits of the second number to compute the 16 bits of the product. Now, this is a signed multiplication, like an imul instruction. And if we change this to mul instruction, then the upper portions of the numbers are going to be zeros and not copies of the sign bit as here. All of them, but only this portion matters, this additional half of the number, because for the 16 bits of the result, only this additional 8 bits of sign extension or zero extension matter. Here we have the number shifted left 2 positions. So it is like this. And when we are adding these numbers together, we have carry from here. So this is going to be 0, 0, 1. And this is the product when we consider these 8-bit numbers as unsigned as opposed to signed. Let's see it in action. We need to put the first number into A register, AL in this case, because this is 8-bit number. And the second number can go anywhere else. We can do the same thing with imul instruction. And now the first half of the result, the lower half, is going to go into the same register where the first factor is. So this is going to be stored into AL register, and the upper half is going to be stored in AH register. If this was 16-bit multiplication or 32-bit or even 64-bit, then the upper half would go into D register, DX, EDX or RDX. So let's take this snippet and test it. Now we perform the unsigned multiplication. The result is FB, and in the upper half 04. As expected. You can also notice that carry flag and overflow flag is set. In case of multiplication, both these flags are set when the upper half of the result is not a correct extension of the lower half. For unsigned multiplication, the correct extension would be 0 extensions, so carry is set when the upper half is not all zeros. And in case of imul, the signed multiplication, the upper half needs to be correct sign extension, otherwise carry and overflow are set. So let's now execute the imul instruction. And we have again FB in the lower half, both FF in the upper half, and there is no overflow. As we just saw, the low portion of the product is the same no matter if we do mul or imul. And that's because the low portion, low n bits of the product only depend on the low n bits of the factors. Therefore, if we have an instruction like this one or this one on x86, this is an instruction that only keeps the lower half of the product and stores it into destination register. And therefore we do not have a mul instruction that would accept this syntax, because it is not needed, because this result, this lower half of the result, is the same no matter whether the multiplication is signed or unsigned. Just be wary that this instruction sets CF and OF flag according to the signed multiplication. And now let's try something different. I'm going to clean this up a little for some experiments. And let's try it with a two-edic number that is not only infinite in the sense of having infinitely many ones, but also has them in a different pattern, for example, alternating digits. We can also write this number as an infinite sum. This is in fact the sum of all powers of 4. And we can use the same trick that we used to find the value of -1. So we separate 1 and extract common factor from the remaining sum. And this gives us that -1 is 3 times this sum, and therefore this is -1/3. So we have two-adic number that seems to be some kind of fraction. We can check it. If we multiply it by 3, we should get -1. So let's try it. Multiplying by 3 is going to look like this. And this is shifted. And if we add these numbers together, you can see that there is only single 1 digit in each column. So this is indeed going to be -1. And so this number is -1/3. And if we add 1 to it, we are going to get -1/3 plus 1, which is 2/3. And we can also shift it 1 bit to the right. And shifting to the right is the same as dividing by 2. So this is 1/3. We could use it as a kind of magic number to divide by 3, because the low n digits of any product only depend on the low n digits of the factors. So if, for example, we take low 8 bits of this number and we multiply another 8-bit number by it, then the low 8 bits of the result are going to be the same as low 8 bits of 1/3 times the other number. And if the other number is divisible by 3, then this result is going to be a correct result of division by 3. On the other hand, when the other number is not divisible by 3, then we are going to get just the lowest 8 digits of some infinite fraction. So this is not a good method of division in general. There are other kinds of magic numbers that are better for this, but this is not in the scope of this video. How can we find this pattern for any denominator? Well, we can try to reverse the multiplication. So let's say that we want to find a number that multiplied by some other number would give us 1. This is unknown. This is unknown. And we can shorten the field a little. We can immediately see that to get 1 here, we need to have 1 here. So the lowest digit in both numbers needs to be 1. This also means that we can only divide by an odd number, because if the number was even, then we would not be able to get 1 here. But this is not a problem, because to divide by 2 we can simply shift 1 digit to the right. So if we want to divide by even number, we can keep shifting until we get an odd number. So if we multiplied just this number by this one, the result would be like this. and it differs from the result that we want to get on this position. So this is the position where we need to flip the bit. And now what we get here is this number. It differs from the preferred result on this position, so we need to flip this bit. Now the difference is here, and we need to flip another bit, and so on. We are going to keep doing this endlessly. But then we are going to get a nice pattern here. And this is in fact an algorithm how we can compute a number that multiplied by 3 in this case, but this should work for any odd number. That gives us 1. Or we could put another number here, not simply 1, and use the same method. Just look for the first digit where there is a difference and flip this bit and repeat trying. Then we are going to keep moving the first difference up. It escapes to infinity. So we are going to get more and more digits of the number. And to wrap this up, I'm going to show you this algorithm implemented for x86. This is a 32-bit version, but you can simply replace all 32-bit registers with 64-bit ones, and it is going to work just as well for 64 bits. Thank you for watching.